Hi, I'm DJ Park, a PhD student at University of Pennsylvania. Today I will present asymmetry in butterfly factory FPGA NoC. Traditional butterfly factory NoC is symmetric, as shown in the figure on the right. When graph workloads are unbalanced, we cannot selectively allocate more bandwidth. We propose asymmetric BFT. It allocates more bandwidth to specific nodes, like this, but it uses similar resources with symmetric BFT. With asymmetric BFT, we expand the design space of soft NoCs. Therefore, users can tailor the NoC to their application, fully exploiting FPGA's reconfigurability. In experiments, asymmetric BFT shows up to 32% improvement in throughput on realistic workloads. Before getting into details, I want to go over some high-level concepts. So when we talk about network on chip on FPGA, there are two categories. One is hard NoC, an embedded NoC on the FPGA, as shown on the right. It's highlighted in yellow. Examples are AMD Xilinx Versal and Acronic Speedstar 7T. Hard NoC is compact in area. It doesn't use programmable resources. Another type is soft NoC, an overlay NoC built on top of the commercial FPGA, as shown on the right. Soft NoCs are more flexible. They can be mapped on any FPGA devices, and the configurations of the NoC can change depending on user application needs. In this work, we focus on butterfly factory soft NoC. The basic building blocks of BFT are T switches that has a single parent port and pi switches that have two parent ports. One interesting aspect of BFT are bandwidth of its level of BFT can be configured by properly selecting T switches and pi switches. So let's say you want to increase the bandwidth in this level. What you can do is you can locate pi switches in this level so that there are more bandwidth in the level we wanted. However, pi switches are more expensive than T switches, and the BFT on the right uses more switch area than the BFT on the left. The first problem that motivates our research is that realistic workloads are sometimes unbalanced, as shown in the figure on the right. And traditional BFT is symmetric, which means that its level is homogeneously composed of either T switches or pi switches. And when you want to allocate more bandwidth to specific PEs, it requires more resources. So in this example, let's say we want to allocate more bandwidth in this subtree. So we locate pi switches in this level, providing more bandwidth in this level. However, pi switches are more expensive, so it uses more resources. This NoC uses more resources than this BFT NoC. So what we want is we want to use more resources in this subtree because we want more bandwidth. But here, we don't need much bandwidth, so we want to use less resource in this subtree. Ultimately, what we want is we want to selectively allocate more bandwidth to specific PEs like this, but using similar resources. In this work, we propose asymmetric BFT that has different bandwidth with similar resource usage. This is an example of asymmetric BFT that has different bandwidth in different subtrees. So type 1 is the most dense and type 3 is the most sparse, and they end up with a different channel width. Therefore, we need a new component, which we call converging switch, that matches different channel width. So the figure on the bottom, this is the zoomed in view of converging switch here. the role of this converging switch is it matches different bandwidth from different subtree. And the simplest thing we can do is we can build this converging switch only with the T switches, but that architecture will lead into traffic congestion on the converging switch. Therefore, we build with T switches, original T switches shown on the yellow here, and T random switches, these orange switches here. What this T random switch does is that when the packet traverses from up to down, the packet is directed lower left one cycle and lower right another cycle randomly. Something like this. So when packet traverses from up to down, the packet can select different path, spreading out the traffic on the converging switch. In evaluation, we run the simulation to compare symmetric BFT and asymmetric BFT. We run the experiments for realistic workloads and synthetic traffic patterns. These are the two symmetric BFT we used, and AS0 and AS1 are the asymmetric BFT we use in the experiments. One thing to note here is that asymmetric BFTs are chosen so that they use less resources than symmetric BFT to perform a fair comparison between the two. In the experiment, this is an experiment result for the realistic graph workloads, and the figure on the right, you see for these benchmark, asymmetric BFT shows better throughput, up to 32% higher throughput compared to symmetric BFT. So the takeaway here is that for balanced workloads, symmetric BFTs are better, but for unbalanced workloads, asymmetric BFTs are better. In conclusion, when the traffic is unbalanced, asymmetric BFT achieves up to 32% and 76% more throughput than traditional symmetric BFT. This work provides more options to the user with the similar resource usage. Remember, the advantage of soft NoC on top of the reconfigurable fabric is that users can customize the NoC to the application. Thank you.